Hello, my name is Gonzalo Berger. I am from Facultad de Ingeniería, Universidad de la República Uruguay, and I will be talking about my work, Hierarchical Matrix Vector Product for HODLR H-matrices, in collaboration with Ernesto and Pablo. So a bit of context on what H-matrices are. They are data sparse approximations of non-sparse matrices. This is the definition given in the pioneer work shown on the bottom of the screen. They are data sparse in the sense that, although not strictly sparse, they require much fewer data to represent them as a dense matrix needs. So instead of a storage space of order n squared for dense matrices, hierarchical matrices only need an order of storage space of n log n. And also operations like matrix vector and matrix multiplication have reduced complexity. Hierarchical matrices present a naturally recursive definition since the matrix is divided in blocks and different blocks are treated differently. So in this case, in the image on the right, the off-diagonal blocks are stored as low-rank approximations of the dense blocks, while the diagonal blocks are recursively divided up until reaching a certain threshold. So one of the most prominent types of H-matrices is the hierarchically off-diagonal low-rank HODLR. These matrices are divided in 4 blocks. Then the off-diagonal blocks are represented as low-rank approximations of the dense blocks. That is where essentially the storage space savings stem from, not only in HODLR matrices, but in all hierarchical matrices. And then the diagonal blocks are recursively divided, since they are also defined as HODLR matrices, up until the block is small enough where we can store them as dense blocks. So in the image on the right, for example, the colored blocks would be the dense blocks, while the non-colored blocks are low-rank approximations of the dense blocks. So this is the representation we used on C for the HODLR matrices, which is based on the HM toolbox for MATLAB. This is a toolbox that allows manipulation for different types of H matrices, among them HODLR. We choose this representation since we are familiar with this toolbox, we have worked before, and also to have a reference of a type, a representation of HODLR matrices, HODLR matrix we know. So in this case, the HODLR matrix is represented as the 2 diagonal blocks. They are defined as HODLR matrices, so that is the recursive part of the definition of the matrix. Then the off-diagonal blocks are represented as the low-rank factors. So for example, block A12 is stored as the 2 low-rank factors U12 and B12, while the off-diagonal block A21 is stored as U21 and B21. We also store the size of the matrix. In this case, we are always working with the squared matrices, so we only store the size, one value for the size. We then store the dense representation of the matrix in the field F. This field is only valid when the block is a leaf, which is represented by the Boolean value is leaf. When the block is a leaf, we only access the dense representation of it, and when the block is not a leaf, we access the 4 different blocks represented by the first 6 values, the first 6 fields. And we also store the rank, which is a value that dictates the precision of the low-rank approximations of the off-diagonal blocks. So the hierarchical matrix vector product for a HODLR matrix is naturally a recursive algorithm following the recursive definition of the matrices. The base case is when the node is a leaf, in which case we compute a dense matrix vector product, since every leaf in a HODLR matrix is a dense block. In our case, depending on which block we are working on of the matrix, we have to do different computations. For diagonal blocks, since they are HODLR matrices, the result is computed with a recursive call, while for all off-diagonal blocks, the result is computed with a low-rank matrix vector product, which is essentially 2 sequential dense matrix vector products using the low-rank factors and the part of the vector that we have to multiply it by. So this would be the code that we have implemented. It's essentially what I was talking about, the base case when the matrix is a leaf. We use the MKL implementation for the dense matrix vector product using the dense representation of the matrix. And otherwise, we have to do 4 different computations, two recursive calls using the diagonal blocks A11 and A22, and then 2 low-rank multiplications using the low-rank factors of the off-diagonal blocks. In this case, the low-rank HMV function is a wrapper that does 2 sequential dense matrix vector products. In the low-rank matrix vector product, the order is important, since if we first multiply, for example, U12 with B12, we would be doing a matrix-matrix product instead of 2 matrix vector products, and that's much more costly. So the order here is important, to multiply first the B low-rank factor with the vector, and then the U low-rank factor with the result of that product. Alongside the hierarchical matrix vector product, we also implement different functions in order to facilitate the manipulation of the matrices and the experimental evaluation afterwards. So one of them is to convert a dense matrix to a HODLR matrix. This allows us to check the levels of precision that the HODLR approximation has for a dense matrix, and also to evaluate the hierarchical matrix vector product with the HODLR representation of that dense matrix with the dense matrix vector product for the original dense matrix. So to convert a dense matrix to HODLR, we assume the dense matrix is represented as an array of values, such as in the bottom of the image. And in that case, we have to map the different blocks of the matrix to that array of values. So in this case, the block A11 is reconstructed as the first half of each row from the first half of rows. So the first half of the array of values contains the first n divided by 2 rows, and from those rows, the first half of each row corresponds to block A11, while the second half of the row corresponds to block A12. While for the second part of the array of values, the bottom half of rows, the left half of each row corresponds to block A21, while the right side of each row corresponds to block A22. Once each block is reconstructed in a dense fashion, then the diagonal blocks are represented as HODLR matrices. So to get that representation, we use a recursive call, while the off-diagonal blocks have to be approximated with a low-rank approximation, in which case we use the SVD decomposition. This is what I was talking about just now. The diagonal blocks are obtained, the representation is obtained by a recursive call to the convert dense to HODLR function, and then the off-diagonal blocks representation is obtained by a low-rank approximation using SVD decomposition. So for the experimental evaluation, this is the platform we have used, and we have generated different matrices. We used originally dense matrices generated using random floating point values, and then we use the function dense to HODLR to obtain the hierarchical matrices. We use different values for the matrices size, rank, and leaf size, and also, since fully comparing the operations with fully dense matrices is not representative of the usage of, or the typical usage of hierarchical matrices, we also use banded matrices with different types of bandwidth, since hierarchical matrices are often used in contexts where the matrix is not fully dense, and instead, for example, matrices like banded matrices where mostly the elements are concentrated near the diagonal. That is a typical case in which the approximation of hierarchical matrices works very well and is typically used. So these first graphs show the relative error of the matrix reconstruction for matrices of size 1024 by 1024. What we call the matrix reconstruction is we generate the dense random matrix from random floating point values. Then we use the function to convert the dense matrix to a HODLR matrix, And then we use the inverse function to convert a HODLR matrix to a dense matrix, which we have also implemented. And then we compare the two dense matrices, the original and the one that has been converted twice. And so this shows the relative error when increasing the rank. We show this because this is not what should be expected. So when the rank increases, we should expect a better approximation, since the rank, a bigger rank means a better approximation of the low rank blocks. What happens here, and which is why we wanted to show, is that in this case the matrices in the left it's a bandwidth of 3 and in the right is a bandwidth of 10, but in both cases the leaf size here is 16. So when we use a rank of 20 and the rank is greater than the leaf size, the behavior there is unexpected, since the approximation, the low rank approximations also have unexpected behavior. So this is the only case in which the precision worsens when increasing the rank. The normal behavior should be something like this, in which when increasing the rank, the precision either stays the same or gets better. So in the right, for example, for a bandwidth of 3, the precision stays the same. It's a quite good approximation of the matrix in no matter what the rank value we have used. In that case, what might have happened is that since the bandwidth is so low, is of 3, all the non-zero values should fall inside a block that is to be represented as dense. So in that case, the rank, which only affects the low rank blocks, should not matter, even if it's very low. And in the right, with a bandwidth of 10, in that case, it does matter the rank. So for a rank of 5, the approximation is quite poor, but when increasing to 10, the approximation is very good, and the change from 10 to 20 is negligible in this case. So here are the execution times comparing the dense matrix vector product with the hierarchical matrix vector product. So the graphs on the left have a rank of 10, the graphs on the right have a rank of 20, and the graphs above have leaf size of 16, while the graphs below have a leaf size of 64. In all cases, the bandwidth is 10. So when increasing the matrix size, we see that the hierarchical matrix vector product, represented by the red line, the increases in execution time are very small. So this is coherent with the execution order of n log n, while the execution order of n squared for the dense matrices also is coherent with the blue line, which is the dense matrix vector product execution times. So we see that the hierarchical matrix vector product consistently attains lower execution times than the dense variant. But we do have to mention here that since we are using banded matrices, the dense matrix vector routine probably does not exploit that fact. So this is a generic routine for matrix vector product, and we are using banded matrices. So we have to mention that as maybe a dense matrix vector routine can attain lower execution times if it does know that it's a banded matrix. But what we have to see here is that the hierarchical matrix vector product does have an order of execution coherent with n log n, and the increases in execution time when increasing the matrix size are not as big as a dense product. So finally, we have executed both routines, the hierarchical matrix vector and the general matrix vector, with a different amount of cores using the GNU part of the MKL library. So what is interesting here is that the the hierarchical matrix vector product, which is the shown on screen, does not seem to benefit from parallelism. So the lowest execution times are usually for the single core execution. This is for matrices of rank 10, lift 16, and bandwidth of 10. And what we attribute this behavior to is that the hierarchical matrix vector product has several executions for smaller matrices. So maybe the call to the routine, to the MKL routine, since it's done on very small matrices and a lot of calls, the overhead of thread synchronization for the routines, the overhead might overthrow the benefits of parallelism, since the parallelism on very small matrices is not that noticeable. In the other case, for the general matrix vector product, the parallelism does seem to benefit the routine, although it does not seem that the 8 cores are always the lowest execution times. But in this case, the executing the general matrix vector routine for different amount of cores does seem to benefit the routine. But we still see that execution times, even when using parallelism for the general matrix vector, are still quite superior to the hierarchical matrix vector product, since in this case we have the y-axis ranges from 0 to 6,000, and for the hierarchical matrix vector product, which I showed just before, it ranges from 0 to 600. So concluding, we have successfully implemented the HMVM routine for HODLR matrices. Both matrix approximation and the routine seem to be highly precise. And also the routine of the hierarchical matrix vector routine consistently attains lower execution times than the Vendon GMV routine, which is consistent with the execution times order, the theoretical execution times for the hierarchical matrix vector, the hierarchical matrices against the dense matrices. And as future work, we intend to broaden the amount of operations implemented for HODLR matrices. So we intend to expand on operations such as matrix multiplications, for example. We also intend to leverage GPU support by devising efficient kernels for implemented routines. Something we have to evaluate here is to migrate to a different representation of the matrix, which is complicated since the hierarchical matrices are essentially a recursive definition, but for GPU implementations, our recursive definition is not the best. So we will try to migrate to a definition that might allow for iterative implementation of routines. And also we have to evaluate other types of HODLR matrix representation. Sorry, I was mentioning just that. And thank you.